Hello, welcome to a video on section 3.5. So we're going to start off by doing derivatives of trig functions. And let's take a look at what the derivative of sine and cosine would be. Now, we do know that a sine graph looks like this. Y equals sine x. You know, a cosine graph looks like that. And you may recall that we did have a homework problem that kind of explored derivatives of sine and cosine functions. And actually, I'm trying to figure out where that was. And I can't seem to remember. I believe it was 3.1. And it's totally escaped me, but that's okay. We could just kind of just look at these functions right now. So anyway, if I take a look at what's happening with sine, we notice that we have horizontal tangents at these locations, and cosine have horizontal tangents at these locations. Also, we notice that we have positive tangents here and negative tangents right there, whereas for cosine we have negative tangents right there and a positive tangent right there. So if I think about it very carefully, the derivative of derivative of sine is going to be cosine x. Why? Well, here's pi, 2 pi, pi over 2, 3 pi over 2. So we know that we have a horizontal tangent at pi over 2 for sine. We have another horizontal tangent at 3 pi over 2 for sine. And we also know that the tangent is positive from 0 to pi over 2. So basically, I'm graphing the derivative of sine here, if you haven't already noticed. Here's x. And then the derivative is supposed to be negative between pi over 2 and 3 pi over 2. And then back to being positive after that. So that's basically forming a cosine graph. Whereas the derivative of cosine is going to be a negative sine x. And why does that happen? Well, do the same thing. So we notice that for cosine, we have horizontal tangents at 0, pi, and 2 pi. Now it's going to have a negative tangent from 0 to pi, then a positive tangent from pi to 2 pi. So it's basically the reflection of sine x over the y-axis. So derivative of sine is cosine, derivative of cosine is negative sine. We can look at it graphically to see why that works. And even you can graph the derivatives too in your calculator, which actually is what I suggested in the notes. So if I were to do that, let me minimize all this junk here. And let's graph sine x, and I already have the derivative all set up under y2. By the way, we have to be in radian mode, very important, as you see in the dialog box. And I'm going to graph in z trig, so it goes from negative 2 pi to 2 pi. So there's a sine curve, as we know. And the derivative graph is coming right now. Oh, look at that. Definitely that's a cosine graph. Or, if I make that a cosine, then graph, there's a cosine graph, which again was the derivative of the sine graph that we just saw. And then the next graph that's coming is like a sine graph, but it's, again, the reflection of sine over the x-axis, because it's negative sine x. So that's what's happening there. Okay. Now, there's actually a proof that we can do for this, a formal proof, which I won't do in this video. I'll do it in person when I see you guys again. But let's look at the derivative tangent. That's going to be the derivative of really sine x over cosine x. So sorry, I didn't mean to write tangent again. Derivative sine over cosine. Okay. So it's derivative sine over cosine. Now, I'm going to have to use the quotient rule. If we use the quotient rule, basically you're going to have to take the derivative of the top, which is cosine x, times the bottom, which is cosine x, minus, that's right, minus the top times the derivative of the bottom, which is negative sine x, and then divided by the bottom squared. So we get cosine squared x, and the two negatives make it a plus sine squared x over cosine squared x. So it's 1 over cosine squared x, or really just secant squared x. So that's going to be the derivative tangent. You can derive it, no pun intended, by doing it this way. And then similarly, if you do like, d over dx of cotangent, which is really cosine x over sine x, or d over dx of 1 over tangent x, and do quotient rule again. I'm not going to do it again because I think it's safe for a homework problem. Is negative cosecant squared x. Or if you do derivative secant, which is 1 over derivative of 1 over cosine, that would be secant x times tan x. So just take me for my word that these are the proper derivatives for those trig functions. Or derivative of 1 over sine x, which is cosecant x, negative cosecant x times cotangent x. So that's what we get there. Okay, let's look at the next page. Example 1. So find dy dx if y equals x sine x plus cosine x. Clearly, we're going to have to use product rule here. So if I do that, y prime, you can just write y prime dy dx, up to you, is going to be 1 times sine x plus x times cosine x, because remember that was the derivative of sine. And of course, you have cosine is negative sine x. Well, those are just going to cancel, leaving this is just x times cosine x. That's pretty simple. Let's look at example 2. You have to find the equation of the normal line. So what we're going to have to do is find y prime, because that will give us the slope of the tangent line. And actually, to be a little more formal, I might write it like this. dy over dx when x equals pi over 4. So first of all, I need to find y prime, which we already know from the previous page is negative cosecant squared x. So now I'm going to do negative cosecant squared of pi over 4, or probably more proper, put a bracket around it and then we'll square it afterwards, because that's really what's happening. Now, if you know your unit circle, which we're going to talk about over here in a little bit, that's 1 over sine of pi over 4. So we have a negative 1 over sine pi over 4 squared. Sine of pi over 4 is 1 over root 2. So it's negative 1 over 1 over root 2. That flips, square it, you should get negative 2. So it means our perpendicular slope of course, is 1/2. So coming back this way, y minus y1 equals m times x minus x1. So you remember doing normal, so we need the perpendicular slope. X minus pi over 4. A cotangent of pi over 4, if you remember, is just going to be 1. And there's your equation of your normal line. And then for example 3, we have to use quotient rule. So you can see how sometimes, quotient rule is kind of important. There's another rule that we can use called the chain rule, and we can turn this into a product where it's cosine x times 1 minus sine x raised to negative 1 power. We haven't talked about chain rule yet. We're going to talk about 3.6. So let's just use quotient rule for now. So u prime will be low d high minus high d low over low squared, and away we go. So low d high, 1 minus sine x, times the derivative of cosine x. So derivative of the top times the bottom, minus high d low over low squared. And again, away we go. So 1 minus sine x, remember derivative of cosine was negative sine x minus cosine x times negative cosine x, because derivative of 1 is 0, and derivative of negative sine x is negative cosine x. So you have negative sine x plus sine squared x plus cosine squared x, because the negative cosine x times negative cosine x is positive cosine squared x. And I'm going to separate 1 minus sine x squared as 1 minus sine x times 1 minus sine x. Well, if you remember, that right there equals 1. That's one of your trig identities. So those trig identities usually don't go away. We don't have to really do the nasty ones, but something we already know. Those go away, and you get that. Okay, lastly, you might remember unit circle stuff. So you are going to have to know some of the basic trig functions, or trig, values of these trig functions, like, that's 0, 1, 0. That's 1, 0, undefined. 1/2, root 3 over 2, 1 over root 3. Or you can say it's root 3 over 3 if you like to rationalize the denominator. 1, 1 over root 2, 1 over root 2. You can also make them root 2 over 2 for sine and cosine for pi over 4 if you want to rationalize the denominator. Root 3 over 2, 1/2, and root 3. So let's make sure you're comfortable with that. Okay, that concludes the notes for 3.5.